Hi, I'm Xiang Yue, a PhD student at UC Berkeley. Today, I'm going to introduce our work, Prototypical Cross-Domain Self-Supervised Learning for Few-Shot Unsupervised Domain Adaptation. The work is with Zhang Wei, Shanghang, Yang, Trevor, Kurt, and Alberto. First, background and motivation. Deep learning has achieved remarkable success in many areas. However, training deep neural networks requires large-scale labeled training data. Yet, in many real-world applications, large-scale labeled datasets are not always available, as labeling is expensive, time-consuming, and difficult. We may consider transferring the model trained on a labeled source domain to another unlabeled target domain. However, direct transfer does not perform well due to the presence of domain shift, which widely exists. So far, a lot of works focus on the problem of unsupervised domain adaptation, where there is a fully labeled source domain and an unlabeled target domain. However, sometimes even getting a fully labeled source is very hard. One example is the diabetic retinopathy dataset, which takes a lot of domain experts to annotate in a long time period. COVID-19 is another example. During the early stage of the pandemic, only few domain experts are available to label the data. To mitigate the above issue, in this paper, we focus on few-shot unsupervised domain adaptation. Instead of assuming a fully labeled source, we only assume few labels per class in the source domain and no labels in the target domain. Next, previous work and limitations. In a previous work, Kim et al. Proposed a two-stage framework, first performing self-supervised learning on source and target, and then performing off-the-shelf domain adaptation methods. During the first stage, they perform in-domain SSL and cross-domain SSL. However, it has several limitations. First, the dataset structure is not encoded well. Second, it's pretty sensitive to abnormal examples. And third, it's unclear how to choose the optimal domain adaptation method in the second stage. Now let me introduce the proposed method, PCS. The proposed PCS framework for FUDA contains three parts: in-domain prototypical contrastive learning, cross-domain instance prototype SSL, and adaptive prototypical classified learning. Now let me introduce the in-domain prototypical contrastive learning. First, for the model architecture, it contains a feature extractor and a cosine classifier. During training, we maintain two memory banks, one for source and one for target. Each entry in the memory bank stores the representation of a sample. After that, k-means is performed and we can get the cluster centers. And we perform prototypical contrastive learning in each domain. Our method is similar to the proto-NCE loss, but ours is simpler. Specifically, we compute the similarity vector between an instance feature and the prototypes in the same domain. Then we compute the cross-entropy loss between the similarity vector and the desired cluster index. Similar to proto-NCE, we perform the clustering m times and get the in-domain self-supervised learning loss. Next, we perform cross-domain instance prototype SSL between instances in one domain and prototypes in the other domain. Similarly, we compute the similarity vector between a sample feature in one domain and prototypes in the other domain. Then we minimize the entropy of the similarity vectors with respect to all samples in both source and target. For the third part of the framework, we use the few-shot labels for standard cross-entropy loss. However, it's hard to learn a good classifier with only too few labels. We further propose to use estimated cluster prototypes to directly update classifier after each epoch. We also perform mutual information maximization between input and output on both domains. Next, experimental results and analysis. We conduct experiments on 4 standard benchmarks with few labels in source and perform various analyses. On Office, with 1-shot and 3-shot labels per class in source, our method outperforms previous best by 10.5 and 3.4%. On Office Home, with 3% and 6% labeled source per class, our improvement is 3.5 and 2.5% respectively. Under different settings on Vista and DomainNet, our improvement is 9.0, 0.7, 13.2, and 3.6%. We perform ablation study, which shows that each component contributes to the final performance without accuracy loss. We also show the sample efficiency, results on UDA with fully labeled source, visualization of features and prototypes, image retrieval results, and quantitative feature analysis. Conclusion and future work. In this paper, we propose a new framework for FUDA, achieving large performance boost on 4 classification datasets, and we hope to apply the method on other tasks.